It was really fun. It's going after.
Okay, so welcome everyone back to this afternoon session. So next talk will be by Jason Lee. He is a fellow here at Simons, and soon he will be assistant professor at CMU. So Jason Lee has done a lot of great works in graph algorithms, and today he will talk about isolating cut, one of the most beautiful new techniques in recent year that I like a lot.
Thanks, Thatchaphol. So this talk will be on isolating cuts, which I will describe as a new tool for minimum cut algorithms. And before I give the talk, I'll give a little disclaimer that all results discussed in the talk will be in a static setting. So we'll make no mention of dynamic graph algorithms. But as we've seen in previous talks in this workshop, there's a close connection between static and dynamic graph algorithms. For example, we've seen that dynamic algorithms often use static algorithms as during initialization or as a rebuilding step. For example, rebuilding a certain data structure after certain number of iterations. And also, static algorithms also use dynamic algorithms to speed up each iteration. But regardless, the focus of this talk will be not so much the setting itself, but the main tool that I'll be discussing, which is isolating cuts. So let's begin with some background on minimum cuts. So a cut is a set of edges whose removal disconnects the graph in some way. And a minimum cut is a cut of minimum cardinality or weight. And the precise definition of minimum depends on the particular variant of minimum cut being studied. In this talk, all graphs are undirected, and we can think of we can either think of the graph as unweighted with parallel edges or weighted with non-negative weights. And finally, so for example, in this case, these are valid graphs that we'll be studying. On the other hand, we will not be studying directed graphs in this talk. So two classic variants of min cut are the global min cut, which is just the minimum weight cut that disconnects the graph in some way. And ST min cut, which is a cut that, given vertices S and T, disconnects to two vertices S and T. And one classic result in this area is that by the max flow min cut theorem, the ST max flow equals the ST min cut. In particular, an ST min cut can be solved by running max flow and then post-processing in linear time. So for example, in this graph here, the following is a global min cut. And here, this is the ST min cut for these vertices S and T. And note that the ST min cut is not necessarily the global min cut. So in this talk, we'll be studying both the running times of these problems, but also the relationship between how these problems relate to one another. So one classic and simple result is that there's a global min cut algorithm that can be solved using many ST min cut calls. And here's the algorithm. So let's fix any S to be any arbitrary vertex, and then just find the ST min cuts over all other vertices T, and report the smallest of these cuts as a global min cut. And note that because there must be a vertex T on the opposite side of the global min cut, we will recover the correct global min cut. And this is an algorithm that solves global min cut in n-1 calls to ST min cut, or equivalently to ST max flow. So this is a brief landscape of the history of global min cut. So first we have an algorithm running at n-1 max flows. And then since then there's been specialized algorithms for global min cut that, for example, in these works, they figure out ways to run max flow quickly. They figure out ways to speed up the max flows on each iteration. And then later on, there's been more faster improvements that run independent of any max flow calls. And finally, a classic result of Krauthgamer showed that there is a near linear time randomized algorithm to solve this problem independent of any max flows. So one famous open problem that Krauthgamer posed in his randomized global min cut work is can we obtain a deterministic global min-cut algorithm to match the randomized running time. But in particular, what's interesting is at that time, even for max flow, it was not known whether deterministic global min-cut algorithm can be solved in deterministic max flow time. So recently, there's been some exciting progress in this area. One classic result, which recently won the Fulkerson Prize, is that deterministic global min-cut can be solved in near linear time for simple graphs. These are graphs that are unweighted with no parallel edges between vertices. This result has been improved and has been viewed in different perspectives, but again, these are for simple graphs. And one result that we'll be studying in this talk is that we showed in the work with myself and Debmalya and Panigrahi, we showed that there's a deterministic algorithm for global min-cut that runs in polylog max low calls. Subsequently, this work by myself has improved the running time of deterministic global min-cut all the way to almost linear, which matches the best running randomized algorithm. This should have been n to the 1 plus little 1. But the techniques are quite different, and we'll mainly focus on the result version. And our main idea I want to study in this talk is the notion of isolating cuts. Formally, to motivate the notion of isolating cuts, let's revisit the simple min-cut algorithm as from before, where we just fix a vertex S and iterate over all other vertices T. And note that really all we need from this algorithm is to find another vertex T on the opposite side of the global min-cut. If we can find such a vertex T, then we have the global min-cut. And then the high-level question we want to ask is how do we efficiently find two vertices on opposite sides of the global min-cut? So here's one simple observation. Suppose that we're also promised that the min-cut is balanced, and let's say it's in the most balanced way possible. There's exactly n over 2 vertices on either side. Then we can just do a random sampling procedure. We'll just sample two vertices S and T, and with probably half, they'll be on opposite sides of the min-cuts. And if that were true, then we would recover the global min-cut. And we can just repeat this log n times to succeed with high probability. So in other words, if the min-cut was balanced, if there were a linear number of vertices on each side, then we can solve this easily in log n many calls to the min-cut. Of course, the min-cut may not be balanced. There could be, let's say, k vertices on the smaller side, where k is much smaller than n. And here, one thing we could do is suppose we sample instead with rate 1 over k, where k might be much smaller than n. Then with constant probability, we still sample exactly one vertex on the smaller side. And once again, we can repeat this log n times to sample exactly one vertex with high probability on some iteration. And finally, we can get rid of this. We can always guess k by doubling, so that's not an issue. But of course, the issue is we may sample many vertices on the larger side. And this is exactly what the isolating cuts problem will try to do. So let's more formally define the problem. So suppose S is the smaller side of a min-cut, and we obtain a subset of vertices T, the sampled set, such that exactly one vertex on the smaller side is in T. And the problem we want to solve is, given the setting, we find for any vertex T in our sampled set of terminals, a minimum cut that separates T from the rest of the vertices. So think of it, you can think of it two ways. You can think of this cut as isolating the vertex T from the rest of the vertices, or you can think of contracting the rest of the vertices into a single super vertex and just running ST min cut. And the catch is we want to output this cut, such a cut, for every single vertex T in our terminals. And we call this the isolating cuts problem. So for example, in this diagram here, for this green terminal D here, the following cut is a valid isolating cut for this terminal. But of course, you want to find the isolating cuts for all the other terminals as well. Any questions about the definition of the problem? So we call this problem the isolating cuts problem. And of course, one naive solution to solving this problem is by simply, once again, contracting all the other terminals into super vertex and finding the SE min cut and doing this for every terminal T. this takes the size of T many Maxwell calls. But of course, the size of the terminals can be large as n. And the key lemma, which we will prove in this talk, is what we call it the isolating cuts lemma, is that the isolating cuts problem can be solved much faster. It can be solved in just log of n many Maxwell calls. So before I cover the isolating cuts algorithm and its proof, let's first discuss how the isolating cuts immediately implies a simple randomized global min cut algorithm. And here the key additional ingredient is just simple random sampling, as we discussed before. Let's kind of guess by doubling the value of k that we want. More precisely, let's iterate over, let's say, log n levels of I, and sample each vertex with probably 1/2 to the I. And let the sample vertex be the terminal set T. And we'll just repeat this log n times to succeed with high probability. And then we'll run isolating cuts on each iteration and return the smallest cut ever found. So the correct is actually very simple. If we take the correct iteration I, then with constant probability on each iteration, we succeed with constant probability that we sample exactly one vertex on the smaller side. And the isolating cuts lemma will return a valid min cut for that terminal. And since we look at all of cuts found over all iterations, we will indeed recover the global min cut. And finally, what about the other cuts we find? Well, they're all valid graph cuts. They're all valid cuts in the graph, so they can only be larger. So taking a global minimum will indeed recover the correct global min cut. And the running time of this algorithm will be dominated by polylog calls to isolating cuts lemma, plus some near linear time post-processing. And therefore, we will show that the isolating cuts can be solved in polylog max flows, and therefore the entire algorithm will run in polylog max flows. So let's see how the isolating cuts lemma is proved. So hold on. Oops. It's not showing it on the other screen. The key idea for the minimum isolating cuts is that we want to first compute so here's a setting. Here, for convenience, we'll rename the terminal set to be R. Think of it as like the red vertices in the graph. And let's say SV is the isolating cut for each red terminal V. And the first idea is we want to compute an upper bound for each isolating cut. So we want to find these cuts, these subsets C of V, which include each SV. So SV is the set of vertices on the side of the isolating cut that contains that isolated vertex. We're going to find an upper bound, kind of C of V, that contains SV. And we also want the CV to be disjoint, to be vertex disjoint. So that's the first step of the algorithm. And to see why this suffices, for each CV, let's imagine contracting everything outside CV to a single vertex, and then T, and then just running the min cut, ST min cut between the terminals and T. And because CV is an upper bound, this will still recover the correct ST min cut. Now, what is the running time of all these ST min cut calls? Note that because the sets CV are disjoint, each edge in the original graph is at most two such graphs, contracted graphs. In the worst case, and that is between two different CV. And if we contract the outside for each of these graphs, it will belong in those two graphs. but it will not belong in any other graph once you contract it. So therefore, the total size of all the graphs, the contracted graphs on which we run ST_min_cut is just at most 2m. And therefore, the total size of the graphs on which we run max flow is also at most 2m. And you can kind of like fold all of these graphs into a single max flow call on a linear number of vertices and edges. So that's the first step of the algorithm. And let's see how we can construct these upper bounds for each isolating cut. So the first step is suppose we compute a set of bipartitions of the terminals such that each pair of terminals is separated by at least one of them. So one easy way that you can see this is possible is if we just randomly partition the terminals into two sets, then with half probability for any given pair S and T, they will belong to different sides. And if we repeat this like log of R many times with high probability, we will there will be one partition that separates S and T, each S and T. But of course, there's also like deterministic ways to do this. For example, by looking at the taking a binary representation of each vertex and going over the bits of the binaries. That's a bit technical. I'll skip this in the talk. And then for each, so in this example, suppose that these red vertices are the 4 terminals, then the following 2 bipartitions indeed separate every single pair S and T. Then for each pair, for each bipartition, we'll compute the min cut separating the 2 sides of the bipartition. So for example, for this bipartition, we can compute this cut here, and for this one, we can compute this cut here. And next, the claim is that if we take the union of all the min cuts we ever found, this separates all of R in the sense that if we delete the union of all these edges and all these min cuts, then every single terminal vertex will be separated from all the others. And this is simply because for any 2 vertices in the graph, there exists some bipartition that separates these 2, and the corresponding min cut will separate those 2 vertices. And since we take a union of all the min cuts, this will indeed separate all the vertices. And now the key claim is that if we remove all the union of the edges of the cuts, then if we look at, for each terminal, the connected component containing that terminal, then it kind of contains the isolating cut. So here, think of the green cut as the isolating cut. The kind of upper bound we obtain is the connected component containing this vertex. And we'll show that this component kind of contains the correct isolating cut. And to prove it is by a simple application of submodularity of cuts, also known as uncrossing. If you look at, this is the bipartition cut, and this is the supposed contradiction that the correct isolating cut kind of went beyond the component here. Then by uncrossing these 2 cuts, we get these 2 cuts, and by the submodularity of cuts shows that if we uncross, the sum of the 2 cuts can be at most the original 2 cuts. And then next, notice that this uncrossed cut here is still a valid cut between these bipartitions. So this value here is at most, this value here is at least the initial min cut between this bipartition. And if we remove these 2 from the equation, we get that the uncrossed cut here is at most the original ST min cut, and therefore we could have replaced this cut here by this cut here because it's also an isolating cut, minimum isolating cut. So we can kind of do this until we find an isolating cut that does not cross any of the bipartitions. Any questions about this? So that concludes the.
There's a question.
I think I'm just missing something. Like, you're saying that we find is this an algorithmic thing or an analytic thing when you're saying that you can have if you have an isolating cut that sort of goes too far, you can replace it with an equally good isolating cut
Right.
that doesn't go too far.
Yep.
Is that an algorithmic thing?
Right. So you can think of it as an algorithmic proof where you kind of replace it each time. So this is purely for in a proof setting. So we're trying to prove that this upper bound lemma. So one way you can think of it as you can just kind of algorithmically replace cuts until they don't cross anymore. Or you can also think of it as take the inclusion-wise minimal cut and and assume for contradiction it crosses over and get a contradiction this way.
Okay, I think my confusion was that your algorithm doesn't know what the isolating cut is, but this is all just to prove a structural theorem. Okay. Yeah, thanks.
So more precisely, the upper bound lemma, this upper bound here is really we're kind of assuming that these SV cuts are inclusion-wise minimal, and therefore they must be contained. So that kind of concludes the isolating cuts lemma. And recall that this immediately implies a very simple randomized global min-cut algorithm, which runs in, if you collect all log factors, it runs in log cubed and many SV max flows. So this algorithm analysis is actually very simple. It's 2 pages. And we discovered this back in 2020 or so. And since the algorithm is so simple and it implies such a natural result that global min-cut can be reduced to polylog SD min-cuts, and since this result was not even known before, we thought we had something special going on. We thought we really had a brand new idea that had potential to be developed in the future. But at the same time, we realized that the concrete result here, global min-cut in polylog max flows, does not imply anything new, because Karger already solved global min-cut 20 years ago. He showed that the randomized global min-cut algorithm in near linear time, which is even faster than even the current best Maxwell algorithms. So unfortunately, we found it hard to sell this result in this way. And instead, the way we sold our result was we showed that you can de-randomize this entire procedure. So in particular, you can de-randomize this vertex sampling here. And the isolating cuts lemma is also deterministic. You can do the bipartitioning deterministically. And the final result we showed in our first paper was a deterministic min-cut in polylog max flows. And this indeed did improve upon the previous best deterministic algorithm. And the new tools we added in this work are pretty standard tools such as color coding, deterministic sparsification, and expanding decomposition. But in spirit, the main the main conceptual contribution of this work really was the simple global min-cut reduction, and in particular the idea of isolating cuts. Any questions so far?
Is the runtime of the deterministic reduction near linear or almost linear?
Good question. It's actually almost linear. At the time, max flow wasn't even almost linear, so we can kind of sell it as near linear. But assuming near linear max flow, it's still almost.
Is that still open? If you can improve that overhead?
Good question. It's still open, but I have ongoing work trying to improve.
Thank you.
So the first row was nice, but in spirit, the real contribution of this work was a simple global min-cut, in particular the isolating cuts. So that gave us hope that perhaps isolating cuts can be applied to a much more broader set of min-cut algorithms, and that's indeed what we found. So in subsequent work, we showed that isolating cuts also we could also apply isolating cuts to solve faster vertex connectivity. This is instead of removing edges from a graph, we want to remove vertices from a graph to this graph. And we showed that with Nanongkai, Panigrahi, Saranurak, and Sorachai, we showed that vertex connectivity can be solved in polylog max flows, which is by the recent breakthrough of max flow, almost linear time. And this was the first improvement in over. Another result we showed was if you consider the more general Steiner connectivity problem, which is given a set of terminals, finding the min cut that separates that set of terminals. We showed that in the same work, essentially by the same construction, so Steiner connecting can also be solved in polylog max flows. And what's interesting about this problem was that there was no previous non-trivial algorithm for this problem. So in the most general weighted graph setting, the previous best result was just the linear max flows. So we kind of had the first non-trivial algorithm that's also optimal. It was also very simple. More recently, we've also managed to apply isolating cuts to various forms of connectivity optimization. This is a problem of finding a minimum weight set of edges to make a graph tau connected for some value tau. This means that we want the min cut of the augmented graph to be at least tau. And our first result was we showed that through isolating cuts, we can solve this problem using polylog max flows. And since then, we further improved it to near linear time independent of max flow and also isolating cuts. Finally, in other work that's not my own, isolating cuts has been extended to more general settings. For example, hypergraphs, symmetric submodular functions, and so on. So, but the story of isolating cuts doesn't end here. Next week, we studied more general variants of min cut. In particular, problems that require us to find multiple min cuts. So two classic problems in this area are the single source min cut, which requires finding, which is given a source vertex S, find the SC min cuts to all other vertices T. And even more generally, the all pairs min cut problem, we're going to find the min cuts for all pairs of vertices S and T. And note that the single source min cut algorithm naturally reduces to n-1 calls to max flows by simply iterating over all T and running the max min cuts. And a classic non-trivial result is that even all pairs min cut can be reduced to n-1 max flows. And this is by a classic result of Amir and Hu. They show that all pairs min cuts can also be reduced to n-1 max flows. This is non-trivial because the trivial algorithm will require n-squared max flows. And the bottom line is single source min cut and all pairs min cut can both be solved using n-1 max flows. And this was the state of the art before our work. So here's like a kind of a diagram of the current landscape, the landscape of min cut problems. At the very top, we have the hardest problem, all pairs min cut, which can be solved in n-1 max flows. This reduces to an easier problem is single source min cut. And an even easier problem, Steiner min cut. And by this recent work here, we show that Steiner min cut is equivalent up to polylog factors to SC min cut. And finally, here we have global min cut using in near linear time by Krauthgamer, independent of any max flows. A recent work in this area showed the following equivalence: that all pairs min cut is actually equivalent up to polylog factors to single source min cut. So in other words, to improve on all pairs min cut, it suffices to improve on single source min cut. So at this point, note that there's kind of like two classes of results here, two classes of problems. The first class will all require like linear number of max flows. And the second class here will all require polylog max flows. And of course, there's also a result here that requires no max flows. And what's interesting about these single source and all pairs max flow problems is that more than 60 years later, these remain the fastest algorithms for these problems. And this is not due to lack of trying. In recent years, there's been fast algorithms for special cases of these problems. For example, unweighted graphs, simple graphs, and various restricted graph families. And in fact, nothing was known prior to our work, even for approximate variants of these problems. So if you want to allow, let's say, 1 plus epsilon approximations for single source all pairs, the best thing you could do was run n-1 approximate max flows. So the first result in this area is we showed that we gave an algorithm for 1 plus answer approximate all pairs min cuts using just polylog calls to the isolating cuts lemma. And this required polylog force. In turn, that requires polylog calls to exact max flow, which is almost linear time by now. So one caveat in this result was that in order to solve approximate all pairs min cuts, we actually required calls to exact max flow. Since then, this has been cleaned up in the sense that it suffices to solve a form of approximate max flow. And this can be solved in near linear time, not just almost linear. This is subsequent work. But of course, the result of exact all pairs min cuts still remain open until subsequent work, where the two groups of the two all pairs min cut groups that were working together, we kind of banded together, and we showed that actually the all pairs min cut problem, or more precisely the Garmer-Hu tree problem, can be improved for the first time in 60 years. The first result in this area, in the first result in this area, we showed that a quadratic time suffices. And indeed, we did follow the recipe of single source min cut. We reduced to single source min cut and showed that this problem can be solved in n-squared time. And here's like a brief high-level overview of how we solved this. We first used black box. Black box used the approximate all pairs min cut algorithm. Plus, if we iterate over all powers of 1 plus epsilon, then we show that we can reduce this problem to the case where we have a terminal set T, and we want to output the ST min cuts, and we want to output the ST min cuts given the promise that all the correct values are within, let's say, a 1 plus epsilon factor of each other. So we kind of reduce this problem by kind of iterating over all powers of 1 plus epsilon. And in other words, our new goal is given the promise that the correct values are all within 1 plus epsilon of each other, output the exact values. This turned out to be non-trivial. And here's a brief overview of how we did it. We kind of used what is known as Steiner tree packing. This is like a generalization of, if you're familiar with Karger's near linear time min cut algorithm, he used spanning tree packing. We kind of we use a Steiner variant of this. We pack Steiner trees instead. And by using this key property that all the min cut values are within 1 plus epsilon of each other, we can show that we can pack enough Steiner trees such that a randomly chosen Steiner tree crosses the min cut in almost 4 edges on average. And here the main ingredients were cut sparsification, this multiplicative weight update method that we've seen in previous talks in this workshop, and also like because Steiner tree is itself NP hard, we kind of instead use an approximate Steiner tree algorithm, and this one in particular was very useful for us. Next, we would sample a log set of Steiner trees to reduce our sample size and still preserve the fact that on average, or with high probability, at least one of these Steiner trees intersects the cut in almost 4 edges. And finally, we showed an algorithm to compute the ST min cut, assuming that there's almost 4 edges in crossing the 4 edges of the Steiner tree crossing this cut. And here the key property we used is that here the key ingredients we used was the isolating cuts lemma, and also like various techniques for treatment. So first step here takes n-squared time because we're running multiple weight update on the sparsifier containing n edges. We might as well sparse the graph first because all cuts are preserved out to 1 plus epsilon. And it's known that there's a form like width-independent multiple weight update that runs in iterations, the number of edges in the graph. And the second step here is dominated by calls to isolating cuts lemma. And therefore, our total running time was polylog max flows plus an additional n-squared running time. So subsequently, in a paper that will be appearing in this Fox, we sped up the Steiner tree packing using advanced dynamic data structures. For example, the robust core data structure that Aaron Bernstein talked about. And indeed, this algorithm is now basically near optimal because we can use the breakthrough result of exact max flow in almost linear time to get Garmer-Hu tree in almost linear time. So basically, we kind of have a satisfying conclusion of all these min-cut problems. We show that all these min-cut problems that we discussed, including the hardest variant, can all be solved in almost any way.
So all of this is 1 plus epsilon?
So all of this is exact.
Exact. Okay. Because earlier you were talking about 1 plus
Right.
epsilon.
The question was, are all these results 1 plus epsilon? Turns out all these results do hold for exact setting. But for the Garmer-Hill tree, or all pairs of min-cut problem in particular, we use approximate 1 plus epsilon as a black box build step towards getting the exact. So in the final slide, I want to discuss future directions for min-cut problems. And the most interesting direction is directed graphs. And so the first natural step we tried was trying to generalize isolating cuts to directed graphs. But unfortunately, there is one issue, which is that the isolating cuts lemma, if you look at the proof of why it works, requires both submodularity and symmetry of the cut function. For directed graphs, we have submodularity, but you do not have symmetry. If we, for any given cut, the direct edges going from one side to the other is not necessarily the same as the edges going from the other side. And actually, it turns out if we play around with definition, we can actually achieve symmetry, but then break submodularity. So it turns out we don't have a definition of for directed graphs that achieves both these properties that are necessary to get isolating cuts to work. And this difficulty of directed graphs has indeed been seen in literature. For example, historically, min-cut algorithms in digraphs have trailed behind undirected graphs. Until recently, the best running time was still MN. And in recent work, we have some partial improvement where we showed that directed min-cut can be solved in just square root n max flows. But of course, this does not seem like the right algorithm. It turns out feel like there's still some slack in this argument, but we don't know how to improve it further. And I leave as an open problem: can we get directed min-cut in Polyglot max flows? Thank you.
Questions for Jason?
Yeah, so Leah and Panigrahi claim that this can, for at least Steiner trees, be extended to hypergraph cuts. Is that something that you think that actually follows on from any of this?
Oh, right. So it does indeed extend hypergraph cuts. For example, global hypergraph min-cut can also be solved in polyglot max flows. But this was not a result that we observed. This was by Chandra Chakaria and Ken Conrad. They observed that more generally for any symmetric submodular function, which includes hypergraph cuts, you can solve in polyglot max flows, or instead of max flows, some kind of symmetric submodular function minimization.
Asymmetric function minimization.
Oh, right, yes.
Or what we just call submodular minimization.
Right, so this result here extends that.
Can you explain what a directed cut is and what we're trying to do in the directed case? Because I failed to understand what's the difference with the undirected case.
So for directed cut, it's not symmetric on two sides. So for example, one concrete way to define it is find a vertex at S such that find a vertex at S, of course, not the entire set and not the empty set, such that to minimize the number of directed edges going out of S. But you don't care about edges going inside S. So for example, the graph has to be strongly connected in order for the min-cut to be non-zero.
If I assume that the max flow is linear time, strongly polynomial time, then will you get everything in linear time, strongly?
Yeah, this is a very good question. So for the first few, so this result, yes. Vertex connected, of course, only works for unweighted graphs. Like this is in a setting where the vertices are unweighted. Each vertex has weight 1. We don't know how to make this work for a weighted vertex activity. I believe this result here does do some scaling approach, so it's not quite strongly polynomial. I might be wrong. It's been a while. This result here, I believe, is also independent scaling. You just directly apply.
How about like Gomerly-Hu tree?
Right.
Mhm.
In Gomerly-Hu tree, so our current algorithm does use some scaling. Does iterative overall powers of 1 plus epsilon. So it's not strongly polynomial. But we suspect that this can be made strongly polynomial. We just we haven't worked out all the details.
Okay, thank you.
More question? All right, then let's thank Jason. Thank you. So we have a break for